Welcome to the Henry AI Labs walkthrough of Keras Code Examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun, generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. This video will explain the latest Keras example implementation of the CLIP model from OpenAI. CLIP is a contrastive learning framework for aligning image captions with the images themselves to do all sorts of downstream applications like representation learning or zero-shot image classification, and probably most interestingly, natural language image search. Natural language image search is such an exciting application. As we'll see later on in the example, this is where you have an image database like all of the images on the internet, or say Unsplash has been a common thing that we're seeing as people are playing around with the CLIP model. But you can have any kind of natural language query and it will find semantic images in the image database. So this is a huge advancement for semantic image search. And in this Keras example, we're going to see how to implement this kind of idea with the Keras library. OpenAI released huge advances in bridging together text and image representation learning. These models were named CLIP and DALL-E. DALL-E is probably more famous because it has this visual component of being able to produce something like an armchair in the shape of an avocado. Given this text sequence, it produces this novel image that does not exist in the training dataset used to train DALL-E. But the other advancement that's really exciting is CLIP, and CLIP might be more useful and practical for immediate applications, such as its ability to do zero-shot image classification, and more recently, just following Twitter and seeing what people are putting out into the open source code world, we're seeing a lot of natural language image searches with the dual encoder trained in the CLIP kind of model design. So it's this implementation in our Keras examples, skipping ahead a little bit in the sequential walkthrough on the Henry AI Labs Keras example series, but it's really important to show that this is coming out. This is January 30th. I'm recording this video on January 31st to showcase how quickly Keras examples is updating itself to keep up with the state of the art. We have things like vision transformer, supervised contrastive learning. Really, most of the things you can think of are being coded up and then integrated in Keras examples. So this should be a really fun walkthrough, natural language image search with a dual encoder. Before we dive into the code, CLIP is building a dual encoder, or a two-tower neural network, one to encode the text sequence and one to encode the image. And this is used to align these two encodings with contrastive learning. The model is then fine-tuned for something like zero-shot image classification in the same way as pattern exploiting training, where you have a photo of a mask and then you insert the different object categories into the mask. So if you're doing 1,000-way ImageNet classification, you'd insert the 1,000 different names for the objects. CFAR 10 be, say, deer, truck, car, cat, those kinds of things. Or maybe you're doing some kind of Kaggle competition or whatever image classification task. But the thing we need to know for now is we have this text encoder. This is a separate neural network as this image encoder. And that's going to be the first step in our dual encoder framework. The first step is to install TensorFlow Hub, TensorFlow Text, and TensorFlow add-ons to use some of the cutting-edge things like the TensorFlow Hub's implementation of the BERT model, as well as some, I imagine some pre-processing functions will be in this TensorFlow Text library, and TensorFlow add-ons for the AtomW optimizer. So TensorFlow Hub, I imagine that a lot of people who watch this video are familiar with Hugging Face, probably honestly are already familiar with TensorFlow Hub as well, but TensorFlow Hub is just a collection of pre-trained models. So this is really interesting because we now have this paradigm of pre-training and then fine-tuning, where we have multi-stage training. So already being able to take something off the shelf, like in text problem domains, you can go into text embedding, transformers encoder text, or BERT is what we're going to be using for this tutorial. But this is the idea of Hugging Face, is you have these pre-trained models. Hugging Face is a little more than that. It also has tokenizers, and it has this really nice modularity of tokenizer, base model head, and then all the community. But this is the idea of these TensorFlow hubs. You have these different models that have been trained in different ways, like the Albert extra large model, BERT trained on Chinese text. And so we're basically just importing this to download the model. Maybe the most interesting detail of this tutorial, or this concept of doing a dual encoding of text and images more generally, is what kind of a data set do we have access to. So in this tutorial, we're using the MS COCO dataset. The MS COCO dataset is really famous for training image captioning models, as mentioned here, as well as object detection, semantic segmentation. Basically, it's a data set of these images that are densely annotated. So they have bounding box annotations for MS COCO. Some cases they have semantic segmentation per pixel labelings, and then they also have captions. So we have 82,000 images, each of which has at least 5 different caption annotations. So for the sake of clip, that means for each of these images, we have 5 different text sequences. So pepper the Aussie pub, and then imagine 4 other variants of this way of describing this image, and then imagine probably more complex images in this MS COCO dataset. So this is where we're getting these pairs of images and then text, and we're going to encode the text, encode the images, and then for each of these 82,000 images, we're probably going to align them with just a single text encoding. So 1 out of the 5 are we're encoding, but then in addition, we're contrasting over, say, 5 times 80,000, 400,000. So there's going to be 400,000 about roughly negative samples that we're going to be using to normalize the image text alignment for similarity, dissimilarity. This is the code used to download the dataset and begin to prepare it for a TensorFlow record object. So first we have the path to get the COCO annotations as well as the COCO images themselves. So we use TensorFlow.keras, the utils.get file, pass in the path to go get the dataset. Extract, I think, means unzip the zip file. And I believe captions.zip is probably the name that we're going to name this once we get it from the internet. So as you run this code, you'll see in the folder icon, if you're using Collab, you'll now have this datasets folder and you'll have the annotations. And then we're interested in this one, the captions train 2014, for the sake of pairing the captions with the images. And then we have the images in train 2014. So I don't think those are downloaded yet. I think we just have the path to them. So we open the annotation file. The annotation file is this file. It's stored in JSON format, which means in this case, as we're looping through the image paths, the image path is going to be pointing to the caption. So the way JSON is structured is it's like dictionary key value. So you're passing in the image path to look up the corresponding captions, and then we're saving these captions in this image path to caption. Collections is like Python data structures, so they have implemented things like dictionaries, queues, decs, or DQs, these kinds of things. So we have our dictionary that's storing the captions that are indexed by the path. So the path might be like, I don't know, / like 1350 dash, something like that, / COCO 2014 dot, like some path like that, .jpg. So we have the image paths, and then we use that to go and find the caption in this JSON structured annotations dataset. So downloading this takes about 6 minutes with my connection, and now we have 83,000 images and the corresponding captions in this JSON file to pipeline into the model. So sorry, last time I clicked on this TensorFlow, this train 2014 folder, and it took a while to open because there's 83,000 images in it. So, all right, so we have downloaded the images themselves. This is the example of the file path that we just described. So COCO underscore and train 2014 / 000009, which corresponds to this image that has image captions like a broccoli dinner or something like that. This is the path that we're using to index the captions folder, which is this JSON file in this block of code. So just to take this apart quickly, X that out. This downloads the data, the annotations, the images, loops through the annotations file, and then we index the path by traversing the directory in the annotations, which is how we did this. And then we take the captions by indexing this JSON file with the path to the image. So hopefully that makes a little bit of sense. So the author of this notebook has more programming engineering skills than I do, and I don't really understand too much about TensorFlow records. So let's go to the TensorFlow documentation and look at TensorFlow records. So in this documentation, they have these 2 star notes to say, sell the idea of TensorFlow records to you. So what I took away from this is it's something under the hood with respect to performance, particularly with respect to the input-output of prefetching data. So there's like when you're doing these pre-processing steps and what goes on the CPU, what goes on the GPU, how exactly the batches are constructed into the training loop, there's kind of a lot of engineering complexity going on behind that. I don't know too much about it, but if you are curious more about TensorFlow records, I don't have too much value to add on this, but I recommend just checking out the TensorFlow documentation. And they have these nodes that sell it. They give you these examples of how to use it and so I think really the high level takeaway is that this helps you save memory, and it's a more efficient way of pipelining the data into the training loop. So now that we have the data, we're going to process it and save it to TensorFlow record file. So we're going to take 30,000 of the 83,000 MS COCO images and use 2 captions for each image, indexing the captions in that JSON file. So first we have the image paths, and now we're going to make the file. We're going to make the directories for our TensorFlow records. So up here we define the TensorFlow records directory is make a directory for TensorFlow records in our root directory. This is this folder right here that we created with this line of code. And so now we're telling the tensorflow.io.gfile.make directories, do it in this file path. So def bytes feature, so again, I don't know too much about this, but so we have the tensorflow.train.feature. A feature we can imagine is like our X and our XY supervised learning, kind of pairing the standard feature label kind of description of this. So we have the bytes list equals tensorflow.train.bytes list, value equals value. So I'd ignore this bytes feature. This has something to do more under the hood with what TensorFlow records is going to do. And there's probably a bit more engineering complexity, but anytime you see bytes, you assume that it means like maybe like almost C++, something under the hood of this. So create example we have for each of our image path and our caption. This is how we turn the feature into caption raw image. And then we have this tf.train.example. So this is the object, the tf.train.example, tf.train.feature. So I might have been wrong with exactly how I said feature is analogous to feature label. It might have something different with that, but tf.train.example could mean the aggregation of both feature in the raw image, caption is the label, but they're kind of both features because we're encoding both the caption and the raw image. If remembering back to what we're doing with clip, we're going to be encoding the text and encoding the images, so we're probably treating them both like tf.train.feature objects. But so anyways, so with this code, I don't have too much to tell you about it. Write TensorFlow records, this is just, I'd treat it like black box code that just is a memory optimization for the sake of implementing these models and for pipelining the data into having a large data set of 30,000 images and 2 captions per image. This is all just things of encoding it more efficiently and getting it into the training loop without having too much bottleneck with respect to batching it and then going and getting the next batch while it trains. In this block of code, we took our images and our image paths and our annotations and we wrote them into TensorFlow record files. And this is better for the optimization with what goes on under the hood between how TensorFlow records hands off the data into the tensorflow.data.dataset object. So now we're going to be creating one of these tensorflow.data.dataset objects. This is the most common object for pipelining data in TensorFlow. We've seen it in all the other Keras examples as well. Examples like from tensor slices to pass data into this object, and other things of just passing NumPy arrays, or from a dataset directory. There's a lot of different functionality in tf.data.dataset in this object. So what we're doing here is we're doing tf.data.tfRecordDataset, and we have the tensorflow.data. And then we map is where you chain these functions onto pre-processing the data. So it has this data, it grabs it, and then it first runs this read example function. So in this read example function, it has tensorflow.io parse single example. This probably has something to do under the hood with the bytes, some kind of C++ code I imagine is going on under this that I don't think we need is relevant to the sake of this clip tutorial with Keras. So then we have the raw image that we get from parsing this from the TensorFlow.records file, and then we have a little bit of pre-processing just to resize it to RGB image, decoding the JPEG, and then resize it to about 300 by 300, and resizing it to 300 by 300 makes it more computationally efficient compared to clicking on that broccoli image earlier. It looks like a pretty high resolution image, so this resizing might be really important. So all that we're doing is we have the data object, this is where it is, then we do these pre-processing functions to it, like this read example function, shuffle it so it's not just all ordered in the same time, in the same order. And then prefetch, I think, means just another argument with respect to what's going on under the hood with respect to how it's batching and preprocessing and parallelizing different operations of getting data ready for our training loop. Now that we've handled the more challenging details of preprocessing the data, downloading the data, and getting it ready for our model, we'll start to do the more fun stuff, which is defining the model. So the first thing that is implemented in this example is the projection from the text encoding and the image encoding into the same space for the sake of feature comparison. So this is common in a lot of contrastive learning frameworks like SimCLR and SimSci and MoCo, where you have the encoding and then you have a separate projection head that projects the encoding into where the contrastive learning loss is applied. So the contrastive learning loss is not applied directly on the output representation. For the text encoding, there's another projection head that takes that representation and puts it into another space to align the representations and do the similarity dissimilarity loss function. So what we're doing here is the syntax of for underscore and range number of projection layers. This will loop through this for this number of times and construct these blocks of computation. So in this case, we have this activation, a dense layer, dropout, and then adding, it looks like we passed in the projected embeddings and the X. So the projected embeddings, we see that we overwrite it with the layer normalization. This might be some kind of skip connection from the previous iteration of this loop. So when we were, say, on the second time of doing this, the first time of doing this, we'll have written this projected embeddings equals layer normalization of the X's that went through the first block. And then when we get to the second time, we're still using this variable name, so it'll pipeline this ahead and have a skip connection in that kind of syntax. So that's how we're constructing this project embeddings layer. We have the embeddings that we're going to get from our vision and text encoding models, and then we have this dense layer to project them, and then this skip connection kind of syntax done with this add into our projection for the loss function. Our vision encoder is going to be using the exception model from Keras Applications. Keras Applications has a bunch of these pre-trained models like ResNets, exception nets, mobile nets, or dense nets, these different kind of convolutional neural network architectures, and probably we'll see the integration of these vision transformers like VIT, botnet, DEIT. We'll probably see that integrated soon as well. But so we're going to be using the exception model to encode the images in the image encoder half of the CLIP framework. So the way that this works is we do keras.applications.exception. We tell it don't include the top, which is the classification layer when it's trained on an ImageNet. Use the pre-trained ImageNet weights. And then for the pooling parameters where you're reducing the spatial resolution of convolutional filter maps, do average pooling instead of, say, max pooling. So then we're looping through the exception.layers and setting them to be trainable compared to, say, having frozen features from a previously trained model. We insert this image, this input layer where we have the shape as we've resized the images previously. Exception has its own preprocess input function, and this is implemented within this Keras Applications thing. So we just chain this together, preprocess inputs, and then exception implements its own preprocessing for the model itself. So now we get the embeddings by running a forward pass of our model. So this is really cool. We take the batch of images and we just pass them through exception by just calling exception like it's any kind of function call, like it's just def sum, return the addition of these two numbers. We just do exception, pass in the inputs, and then we have our embeddings. So our embeddings in contrastive learning are the batch size by the output vector dimension. So this might be like a matrix of, or a tensor of batch size by, matrix of batch size by the embedding dimension. So we have a matrix where it's we pass in 32 images, and then each one gets transformed into a 512 dimensional vector. We have a 32 by 512 in this embeddings matrix. So now we're similarly going to call the project embeddings function where we just defined it up here, and we're going to have these special parameters for defining it in our vision encoder because we might want to have different projection parameters with the text head compared to the vision head. So then all in all, we put this all together, inputs, outputs, we see how the inputs is here, and then we see how we chain together inputs gets passed to inputs here, and then exception input gets passed to embeddings here, and then outputs takes the embeddings here. So we have this pipeline of chaining the input, passing it through these different layers, and then we return the Keras model. Now that we've defined the vision encoder by using the Keras pre-trained exception model and some of the implementations of exception like its own pre-processing layer, we're going to now also use BERT from TensorFlow Hub. And again, this is how we're going to be encoding the text sequences to be aligned with our image encodings as well. So the first layer is from hub.keras layer, we have a text pre-processing layer for BERT. So this is really important because there is a lot that goes on with respect to pre-processing text data. Images are more natural to process or to pipeline into deep learning models because they're already height by width by RGB generally, and you just kind of put that into the model. Whereas with text, you first have to turn it into numbers. You have to turn this to calculate the loss, we compute the pairwise, into something like 0, 1082, 10,731, things like this in order to put it into a deep neural network. So the way that that works is text preprocessing kind of has like two stages. The first stage is where you clean the data. You do things like regular expression filtering, lowercase it, get rid of any kind of crazy characters that have appeared if you're scraping data from the internet or something. And that kind of like cleaning it, just making it in the rawest form before it's tokenized. And then the second step is tokenization and building the token to index mapping. So tokenization is where you split the words up, say pairwise turns into pair and wise. Similarity might turn into similar and then hyphen arity because that can be used for other kinds of words or slash like ing slash ed, these kinds of things with how you tokenize the data and split it into these little parts. So then the tokens are used to index a position into the BERT vocabulary embedding table. So this is the first layer of BERT. With BERT, the first layer of it, it has the length of the vocabulary size, and then each column is the embedding vector for that word or token. So you turn these inputs into numbers, and the numbers index the vector in the input layer to something like BERT, GPT, or any of these. Even an LSTM would do this. Hopefully that was a decent explanation of how text is pre-processed for these natural language processing models, and I highly recommend learning more about that before diving into something like CLIP, unless you're just kind of really curious about this and just want to get the first model trained and have a sense of this example. So then what you do is you use the BERT model that's been pre-trained on the TensorFlow Hub, just downloading the model with this, and then similar to any kind of function call, we just have BERT, and then we just pass the inputs and we get our embeddings. So the next thing that's interesting about this is the indexing of the pooled output. So BERT has these different outputs on its output layer. So pooled output is one way of indexing this output layer, because the way BERT is pre-trained is it has an output on every single index position on this output vector layer, because it's masking out tokens and then it's predicting what's been masked at this position. And then you also, in the BERT pre-training, you have the CLS token, which is where you do this next sentence prediction task. And then in things like Squad, they might index this to say, this question is not answerable, that classification. They could do things like this. The CLS token is used to, sometimes you would average along the CLS token, like similar to when you average out word to vector embeddings to make a sequence representation. You might do that to represent the sequence of BERT, something like that. But pooled output refers to pooling this entire vector, or it could mean this, I'm not exactly sure, but pooling the output, just all I'm trying to communicate is to have a sense of BERT has all these different, like you would index different locations in the output as you're pre-training it, and then therefore there's a decision about how are we going to repurpose this when we're fine-tuning it. In our case, we're doing this for contrastive learning, where we're just trying to form some kind of semantic embedding of our text. So it might be natural to do this CLS token indexing or the pooled output, which I think means just doing this like a one-dimensional pooling along this output where each vector is pooled, and then you get like a reduced dimension vector. It could be pooling along, it could be like a matrix at this output too, where you have the length of the output and then the hidden dimension or the output dimension. So that's kind of the idea of pooled output. Terrible explanation, but that's the idea. High level is that there are different outputs with BERT and how you're indexing them. So now that we've defined the vision encoder and the text encoder, we're going to put it together in the contrastive learning framework, where we're comparing the similarity between an image and its text caption, as well as all the other text captions in the batch. So it's very important to note that when you're implementing these contrastive losses, similar to the SimCLR algorithm, you're implementing this as a batch loss. We're passing in a batch of images and a batch of text captions, and we're doing this batch matrix multiply where we have these huge matrices with the similarity. So we're kind of indexing along the diagonal in these matrices. So that's probably, in my opinion, that's where the complexity comes when you look at reading these, the code for contrastive learning papers like MoCo or SimCLR. The complexity is in how they do these large batches and index them to extract the similarity over the denominator of all the other pairings. So we'll walk through this. So we start off with a text encoder, image encoder, just passing it in. Temperature is just a way of smoothing out similarity. So when we're calling this to get out the caption embeddings, image embeddings, basically just go to the GPU, and then the idea here is that if you have two GPUs, then you put the caption encoding on GPU 0, image embedding on GPU 1. So that's just a subtle thing. I imagine most of us don't have two GPUs for this. So we're computing the loss now. We have the caption embeddings and the image embeddings. So caption embeddings is a huge matrix of all of our images or all of our captions, and then the embedding output vector dimension of our BERT model for captions and our exception model for images. So we have this huge matrix of the number of images by the output dimension. So the first thing that we do is we have the logits, where we do the matrix multiplication between these two gigantic matrices of the caption embeddings and the image embeddings. So the key throughout the rest of this is how we're going to be indexing this output to get the correct positive pairs over the negative pairs in the loss function. This first matrix multiplication are the logits of the output. This is the y-hat, or the predicted similarities between the captions and the images. So this is the prediction of our model, is the alignment between the image embeddings and the text embeddings. So this is our y-hat. How do we construct our ground truth label y, which is how we want to maximize these similarities along this diagonal and signal that to the loss function of the model. So this is going to be a little complex, and I probably should, get like a drawing that I can do to do this, but I'm not sure exactly what software to use for that. If you have any suggestions and you're still watching the video, please link it in the description or suggest it. So anyway, so we have the image similarity and we have the caption similarity, and we're going to add these two together to form the targets. So exactly how does that work? First we have this, the embedding matrix, which is the number of images by the embedding dimension. And as we multiply that by itself, then along the diagonal, we just have like I1 times I1, but then the rest of the matrices, we have I1 by I2, I1 by I3. And what we're going to do is we're going to average along each of the index positions to get the average distance of I1 with all the other images. And we're going to do the same thing with the target, where we get the multiply target by itself, and then we have the average distance between the target and all the other text encoding. Sorry, the T is mixing me up and making me think it says target. But we're getting the average distance between the text encoding and all the other text encodings. We're doing a similar kind of matrix multiplication. So we have the average distance of each image from all the other image embeddings, as well as the same thing with the captions. So then we add these two matrices together, and then we have this normalization where not only do we have I1 by T1, we also have like this normalization where at this position, the T1 has been, the representation of T1 has been normalized by computing its distance from these other text encoding. So it's a little more structure to this loss by also having the average of the text encoding. So I recommend maybe just on like a piece of paper, just doing two matrices where you have, say, like 1, 2, 3 for your images, and then just do 1, 2, 3 by 1, 2, 3 matrix multiplication, and then have another one where you have 4, 5, 6, or something like that, and for your text encodings. And just do that matrix multiplication, add the two matrices. That's probably the best way to get a sense of this, is just to do it out by hand. But I'm not sure what software to use to do this by hand in this video, and I'm being a little lazy. So anyway, so that's how you get the Y true. That's how you get the similarity, is by doing this distance and then adding them together to index this position of the ground truth, make these more similar, and then get the correct, what is predicted for the I2 by T1, I3 by T1, and so on. So that's how you construct this Y hat minus Y, and then you use just categorical cross entropy along each index position of the matrix. So that's the key to these contrastive learning frameworks, is you implement these as large batch losses. That's the idea of SimCLR, is you have this large batch, and so you have to implement the similarity denominator comparison by indexing these matrix multiplications. Hopefully you're still with me after that. Not the best explanation of how this works, but we have this similarity alignment, and hopefully the high level motivation of we're trying to have this ground truth of just multiplying all these images by all these text encodings, image encodings by text encodings together, and then how we construct the signal to try to make this more similar to each other and this bit less dissimilar by using the categorical cross entropy between these two Y hat and Y matrices. And we have to construct the Y matrices by multiplying out the caption embeddings and the target and the image embeddings, and then adding them together. So then what we do is we have our training loop, we have our gradient, we just pass it in the features to get the embeddings, and then we have the self.compute loss, which is this thing, and then we have our gradients, optimize or apply the gradients, tie it together, the gradients and the trainable variables, and then we update our loss tracker with this return loss, and then we have our test set. So now that we've defined the vision encoder and the text encoder, and we have the dual encoder, which is how we tie together the text encoder and the vision encoder and apply the contrastive loss on the outputs, we have this code to define the models and then to compile it into our training loop. So maybe one key observation here is the number of epochs. What I'm finding is it takes about 15 minutes for an epoch on this Collab GPU, and then we have a batch size of 256 images and text captions. So this is really important because, again, the batch size is going to be the number of image encodings and the number of text encodings. So these batch sizes, we implement these batch losses in these contrastive learning frameworks. So if you take away anything from this video, I hope it's just that you understand this idea of having these large batch loss functions and having to index them for implementing these contrastive learning frameworks, like CLIP or SimCLR or MoCo uses a bit more of a sophisticated way with the memory bank, but it's still this idea of having these large batch matrix multiplications. So we have some hyperparameters on our vision encoder, the number of projection layers with respect to that projection into the space where the loss is applied. So you have the vision embedding that comes out of exception, or the text embedding that comes out of BERT, and then you project that into another space with a multi-layer perceptron-like architecture, and these are the hyperparameters that define that. Training this model takes about a little longer than an hour to do 60,000 image caption pairs with 30,000 images and 2 captions per image. So it's interesting to think about just this big data problem and getting more of a sense of what we're talking about or what we're reading about when we see these papers that talk about large-scale experimentation like this. So overall, we have 60,000 image caption pairs, the 30,000 duplicated twice to be paired with the text captions using a batch size of 256, and then using this V100 GPU offered by Collab. It takes us about an hour to get through, or an hour and a half to get through 5 epochs on this data. So in deep learning, it's common to see, say, like 100 epoch training, or maybe even 800 with some of these self-supervised learning papers. So just getting a sense of how multiple GPUs are needed, long times to really achieve these amazing armchair in the shape of an avocado. You're not going to get that with an hour and a half of training. But these are the loss curves. We see the validation loss going down with our validation set of aligning the similarity of text-image captions. Here's another interesting takeaway from this tutorial. We talk often about model compression and speeding up inference time, and now we're seeing it in this case. So we're trying to have our vision encoder encode 83,000 images with our model by just doing this as a function call where it's .predict, and then you pass in the data. This is the TensorFlow.dataset from tensor slices, and then we pass in the path, and then the map is where it processes the path to read the image. So you pass in the path. The map is like chain on this pre-processing to as the tf.data.dataset object loads this data path, and then batching it. So this takes about 12 minutes just to encode this many images. So before we can even use our natural language processing search to search through the image embeddings, it's going to take 12 minutes to run inference and form vector embedding encodings for all of these images. Now that we've run inference through all 82,783 images, we have a feature bank of 82,783 images by 256, which is the dimension of our image encodings. So when we were talking about deep learning search engines or having this semantic representation, we construct these feature banks, or these in these information retrieval papers, you'd call this a document index, as you're encoding each of, say, scientific papers or websites, stuff like that. And so this is our feature bank that we're going to be using to have a query and then go find which vector is out of these 82,000 vectors are the most similar to our query vector. The motivation for our large-scale image search engine is that we could query these really odd images or have really specific things like a dog dressed up in a football jersey, some crazy query like that, and it searches a massive image database such that we can find these images. So in order to search through these feature banks by doing vector similarity, a lot of implementations have been made that do GPU optimization. So similar to if you've seen how much faster TSNE runs on Rapids compared to a CPU sklearn, they're doing the same kind of thing for vector comparisons on GPU. So I think the Facebook FAISS face, this is the most popular library, I think, for doing this. But in this case, what we're going to be doing is just matrix multiplication, L2 normalization, in order to just do the dot product similarity. But this is 83,000. If you're doing, say, I've been experimenting with the Core 19 dataset where it's these papers related to COVID, and it's 400,000 of these papers. So once this becomes 400,000, and say you want to increase the embedding dimension as well, you're going to want to use stuff like this in order to do vector similarity search. Again, this is the goal of our system. We have a query, a family standing next to the ocean on a sandy beach with a surfboard, and we want to find matches in the MS COCO dataset. So we have as a reminder, BERT already has this text preprocessing layer. So as we convert this into a list and then pass it into BERT, BERT is going to clean it, tokenize it, and do all that under the hood with how we define our text encoder. So this is how you run inference, find matches. You can just pass texting like this because of this really great modularity with the syntax of the BERT preprocessing and all that, the image embeddings. And now we have our nearest neighbor images with our text query. So this is just an amazing application. This is one of the applications of Clip. Clip is also being used for, as shown here, for zero-shot image classification, but also maybe the search engine application is probably what will be more used. So now that we've learned these representations of images and text, we have to think about how we want to do self-supervised representation evaluation. So one common way of doing this is to do a k-nearest neighbors classification on top of the feature banks. This is commonly used in like SimSciM, all the contrastive learning for images papers. They look at, I don't know if they do this in the paper, but a lot of these, you've seen like the Lightly open source self-supervised learning library, they describe how they use k-nearest neighbors evaluations of the representations during training. But anyways, the idea is basically just you have k-nearest neighbors. K-nearest neighbors is just you go and get the 3 or k most similar vectors, and then you just use, say, the average or the weighted average of their class labels to build a classifier and run inference on some new image. So what this is doing is it's showing the ability of this to label these images, and In this case, it's not labeling it like cat, car, dog, that kind of thing. It's just seeing if it's retrieving the correct caption on the validation set. Thank you so much for watching this explanation of the natural language image search with a dual encoder from the Keras examples. We saw how to install the TensorFlow Hub, TensorFlow Text. We used the add-on for the optimizer. We saw how to get the MS COCO dataset, download it, and get the captions, and then also prepare it for this TF record file. I didn't know too much about TF records, but if you are curious, this is the TensorFlow documentation on it. I mean, we didn't run out of memory once while we were doing this, so I imagine it has, and it was pretty fast training time. So this has to do with the memory and the batching optimizations. So if you are interested in this, I highly recommend learning more about it. How we go from TF records to TF.data compared to just say going from TF.data from NumPy arrays or just directly from the directory. So we saw how this looks, and then we saw how to put this into our TF.data object. And then we saw the projection head implementing the model. Projection head is how we go from the output of the vision or the output of the text encoder into a separate space to apply the contrastive learning loss. So then we saw how to use Keras applications to grab the exception model, how to use the preprocessing that's already been implemented in this. And then we saw how to do a similar thing with the BERT model. We abstract so much of preprocessing away by just doing preprocess equals hub.keras layer. So compared to having to write our own tokenizer, our own cleaning, token to index mapping, we just wrap this in preprocess and it makes it all so much easier. So we saw how to implement the contrastive learning framework. And again, my explanation of this wasn't great because it's pretty complex I guess it depends on what level you're at, but it is this large batch loss function and you have to have this alignment. So there is a bit of skill involved in knowing how to align the predicted logits with the ground truth targets for applying this similarity loss. We saw how to actually construct the vision encoder, text encoder, pass this into the dual encoder framework. We saw the hyperparameters on this projection embedding head that's defined up here. And then we ran the code in this model. You train it for 5 epochs, and you see the validation loss continuing to decrease with the training loss. And you imagine this would do even better if you had maybe a smaller learning rate, something like that, and trained it for longer. But we're training it with 60,000 image caption pairs at a batch size of 256, and it can all run on the Google Colab GPU, which is really cool. So then finally we put it all together and we saw how inference time through 82,000 images takes about 12 minutes. It's not these optimizations for inference time. This is no joke. It's important to have fast inference, especially this is only 83,000 images. As we talked about in the intro of the video, this idea of natural language image search is so exciting, but you need to have a massive collection of images in order to really find these nuanced pairs. And maybe we could see it being coupled with DALL-E to produce these images, all these kinds of things in the generative data augmentation space. That is really just a lot to think about. So then we saw an example of how to use it, how to insert a query, and then how to play around with this model using the MS COCO dataset. And then we saw this quick example of one common way to do self-supervised representation evaluation is to see how well these features perform in k-nearest neighbor classification. Thank you so much for watching this video. If you're interested in the rest of the Keras Code Example series on Henry AI Labs, this is linked in a playlist, and also this is what the original Keras examples looks like. So thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.